Deep below the stately new public offices in Whitehall, London, lies the Cabinet War Rooms. Throughout the Second World War, this underground bunker served as the nerve centre of the British war effort, allowing Prime Minister Winston Churchill, his cabinet and their support staff to carry on working through even the heaviest German bombing raid. It was also the home of one of the great unsung technological achievements of the Second World War. Tucked into a back corner of the bunker is a small, nondescript room, no larger than a broom closet, its door fitted with a sliding vacant/occupied sign. Despite appearances, this was not a private bathroom for taking Churchill-sized dumps, but rather one terminal of an ultra-sophisticated telecommunications system that allowed the Prime Minister to speak directly with his American counterpart without fear of their conversation being intercepted. A marvel of 1940s electronics, many of the technologies pioneered by this system are still used to this day. This is the incredible story of SIGSALY. The story of Sig-Saly begins in 1928 with Homer Dudley, an engineer at Bell Telephone Laboratories, who was searching for a means of compressing human voice signals so more could be transmitted over the same telephone lines. In the course of his research, Dudley determined that human speech is composed of a bass carrier wave generated by the vocal cords, whose harmonics are modulated by the changing shape of the speaker's mouth and further modified by the creation of unvoiced and plosive sounds like P, B, T, and D. This creates a great deal of redundancy, greatly increasing the bandwidth needed to transmit any given voice signal. But if, Dudley realized, human speech could be broken down into its fundamental sounds and the redundant portions stripped away, the resulting digitized signal could be more easily transmitted through a telephone line and reconstituted at the other end. Furthermore, the signal could be compressed into a certain narrow frequency band, allowing a greater number of signals to be transmitted on different bands through the same line. To this end, over the following decade, Dudley developed a device he called the vocoder, a combination of the words voice and encoder. First patented in 1937, the vocoder worked by passing a voice signal through a series of band-pass filters, which broke it down into a number of frequency bands and measured the intensity of the signal within each band. This created a greatly simplified, digitized signal that could be more easily transmitted through a telephone line or over the radio. At the other end of the line, a device called decoder reversed the process, constructing the original signal from its basic elements. While the reconstituted signal was rather robotic sounding, the vocoder represented a huge advance in telecommunications and pioneered the now ubiquitous technology of digital signal processing. In 1938, in order to demonstrate the possibilities of Bell Labs' revolutionary technology to the public, Dudley and fellow engineer Robert Rice modified the vocoder to create the world's first speech synthesizer. Known as the voder, short for voice operation demonstrator, the voder was essentially a vocoder system with the encoder removed. In its place was installed a piano-like keyboard assembly which could generate one of two sounds, a buzzing tone to represent the bass carrier wave produced by human vocal cords, and a hissing sound to represent voiceless frictive sounds like S or Z. The operator could switch between the two sounds using a pivoting wrist bar and vary their pitch using a foot pedal. Meanwhile, the set of 10 keys connected to the band-pass filters allowed the operator to modulate the frequency of these inputs and mix them together to create dozens of other sound combinations. By combining all these different elements together, the operator could generate nearly any spoken sentence, albeit in an eerily robotic tone. If this sounds incredibly difficult, that's because it absolutely was, with only around 20 Bell Lab demonstrators or women attaining a sufficient level of proficiency on the voder to produce intelligible human speech. The voder was a star attraction at Bell Labs' pavilions at the 1939 New York and San Francisco World Fairs, with packed audiences marveling at the modern miracle of fully synthesized speech. And for more on another technological wonder of the 1939's World Fair, please check out our video, The World's First Celebrity Robot, on our sister channel Highlight History. The outbreak of the Second World War that same year brought with it an urgent need for secure voice communications. While nearly all militaries at the time had secure encryption systems for sending messages by Morse code, for example the infamous German Enigma cipher machine, this was often a slow process, and military commanders preferred to speak to each other directly over the phone. Methods for scrambling voice communications had existed since the 1920s, based on the principle of frequency inversion. Such scramblers converted high frequencies into low frequencies and vice versa, rendering the signal unintelligible. At the other end of the line, a descrambler circuit reversed the process, constructing the original sound. But while the scrambled signal was unintelligible to the average eavesdropper, the descrambling process could easily be reversed reverse engineered by any technically minded individual. Indeed, Bell Labs, who developed the technology, insisted on calling it a privacy rather than a security system, and included the following warning in their initial technical report. This device was thus an effective privacy arrangement against the casual listener, but was very easy to crack even in those days. An inverter can be built by any reasonably competent high school boy, and in fact, there have been instructions on how to build one in QST magazine. Consequently, in the 1930s, Bell Labs developed a more sophisticated system derived in part from Homer Dudley's vocoder technology. This system broke the voice signal up into 5 different frequency bands, rearranged the bands, and applied frequency inversion to some of them, resulting in 3,840 possible combinations. Of these, however, field tests revealed that only 6 combinations actually rendered the signal unintelligible. In the finalized system, a new scrambling combination or key was applied to the signal every 15 to 20 seconds, with the key being recycled after 36 steps. The finalized scrambler, known as the A3 speech privacy system, was officially adopted by the US government and military, and by 1941 was used in nearly all secure communication lines, including the radio telephone link connecting US President Franklin D. Roosevelt in Washington, D.C. to Prime Minister Winston Churchill in London. But despite its increased complexity, the A3 was still vulnerable to a determined codebreaker. Indeed, in the build-up to the war, the Deutsche Reichspost, aka the German post office, set up a listening post in Noordwijk in the Netherlands to intercept Allied A3 radio telephone traffic. By analyzing this traffic and examining a commercial version of the A3 scrambler, in September 1941, Reichspost engineer Kurt Vertelein succeeded in cracking the code, creating a device that could descramble Allied signals in real time. Unbeknownst to the Allies, the Germans would continue to listen in on A3 scrambled telephone calls for the entirety of the war. The vulnerability of the A3 scrambler system would have serious consequences for the Allied war effort. For example, on the morning of December 7, 1941, US Army Chief of Staff General George C. Marshall received a decrypted Japanese diplomatic cable indicating that Japan had abandoned all political solutions to its conflicts with the United States. This included that Japanese attack on US forces was imminent, and Marshall scrambled to alert his Pacific commands, including Pearl Harbor in Hawaii. However, Marshall doubted the security of the A3 scrambler system and instead chose to send his warning via coded radio telegraph. Tragically, the message arrived after the Japanese surprise attack on Pearl Harbor had already concluded. Such incidents clearly demonstrated the need for a more secure telephone encryption system, and Bell Labs soon began work on a replacement for the A3 under the codename Project X. This effort was directed by A.B. Clarke, later a founding member of the National Security Agency, or NSA, with the assistance of British mathematician Alan Turing, who would become legendary for his role in breaking the German Enigma cipher. Like the A3 scrambler, Project X was based on Homer Dudley's vocoder technology, using a process called pulse code modulation, or PCM, to sample the input signal 50 times per second and dissect it into 12 separate channels representing 10 different frequency bands, the pitch and amplitude of the signal, and whether a given sample sound was voiced or unvoiced. Once encoded, a cryptographic key was then applied to the signal in order to mask it. This key consisted of a set of 16-inch phonograph records onto which was recorded random white noise generated by a mercury vapor rectifying tube commonly used for converting alternating current to direct current for use by streetcar motors and other industrial equipment. The addition of this random noise rendered the transmission signal completely unintelligible. At the receiving end, a duplicate set of records was used to subtract the noise from the signal, allowing the original transmission to be reconstructed. Each conversation used a different, completely unique pair of enciphering records, each given a code name like Red Strawberry, Wild Dog, or Circus Clown, meaning that even if the enemy somehow managed to capture one record, it would not compromise other networks. After each conversation, the records along with their original master recording were destroyed and another set substituted, effectively turning the system into a giant electronic version of a one-time pad, the most secure type of cipher. Originally made of ordinary vinyl, the records were later changed to more durable aluminium-backed acetate. A successful decoding of the signal required the 2 cipher key records to be precisely synchronized. The turntables featured more robust construction and sophisticated speed controls than their commercial counterparts. They were also only tuned on precise times, synchronized through the use of a standard local time signal, such as those standard timing signals transmitted from the US Naval Observatory in northwest Washington, D.C. As each phonograph record held only 12 minutes of sound, each terminal had 2 turntables, allowing one record to be cued while the other was still playing. The finalized Project X terminals were massive beasts containing 384 vacuum tubes in 40 racks and weighed 55 tons, occupying 200 square meters of floor space and requiring their own special air-conditioned rooms to dissipate the 30 kilowatts of power that they consumed. In early 1942, Bell Labs demonstrated Project X to the US Army, who were sufficiently impressed to place an order for 2 complete systems. In Army nomenclature, the device became known as SIGSALY, which was not an acronym, but rather a random US Army Signal Corps codename designed to look like one. The system was also informally known as the Green Hornet, as the buzzing sound of the encoded signal resembled the theme tune of the popular radio show of the same name. The first SIGSALY terminal was originally to be installed beneath the White House, but President Roosevelt, aware of Prime Minister Churchill's annoying habit of calling at all hours of the day, had it moved to the Pentagon, with extension lines later added to the White House and Navy Department building. The other terminal, being too big to fit in the cabinet war rooms, was instead installed in the basement of Selfridge's department store on Oxford Street in London, with extensions to the US Embassy, the Prime Minister's residence at 10 Downing Street, and the cabinet war rooms. In the latter location, the telephone receiver was installed in a former broom closet, disguised as a bathroom by the addition of a sliding vacant/occupied sign on the door. As no transatlantic telephone cable existed yet, the encoded signals were transmitted between the US and the UK via radio telephony. The first official conversation over the transatlantic SIGSALY hotline took place on July 15, 1943, attended by high-level American military personnel, including Lieutenant General J.T. McNarney, Deputy Chief of Staff Lieutenant General Brehan Somervell, Commanding General Army Services Forces, Lieutenant General J.L. Devers, Commanding General European Theatre of Operations, and others. As the Allies advanced across North Africa, Europe, and the Pacific, additional terminals were installed in Algiers, Brisbane, Hawaii, Oakland, Paris, Manila, Guam, and after the Axis surrender, Berlin, Frankfurt, and Tokyo. A terminal was even installed aboard a 250-ton ship called the OL-31, providing General Douglas MacArthur with a secure mobile communications hub during his Pacific Island topping campaign. The SIGSALY network was installed and maintained by the 805th Signal Service Company of the US Army Signal Corps, an elite unit comprising 81 officers and 275 enlisted men, handpicked and specially trained by Bell Labs personnel. These technicians faced a daunting task: the fiendishly complicated and temperamental SIGSALY terminals requiring near constant maintenance and adjustments to keep them running properly. Over the course of the war, the SIGSALY system hosted some 3,000 high-level Allied conferences, none of which were ever decoded by either the Germans or the Japanese. Indeed, while the Deutsche Reichspost, previously so successful in decoding the A3 scrambler traffic, frequently intercepted SIGSALY traffic, they assumed it was some sort of sophisticated telegraphic cipher system and made no progress in cracking it. As a testament to the system's effectiveness, when the Allies invaded Germany in 1945, they discovered a Reichspost communiqué from July 1943 stating that there is not much to be gotten from the Allies now. The SIGSALY system was dismantled in 1946 and remained a closely guarded secret until 1976, when the American Telephone and Telegraph Company, or AT&T, parent company of Bell Labs, sued the US military under the Freedom of Information Act in order to gain access to some of the original SIGSALY patents. The US government and military continued to use vocoder-based technology for secure communications until the 1960s, with the K06 and HY2 systems replacing the bulky records with pseudo-random number generators and using transistorized circuits to bring the system's weight down from 55 tons to a more manageable several hundred kilos. However, these largely analog systems suffered from poor sound fidelity, making them difficult to use, and by the 1970s were replaced by better, fully digital systems. Though largely forgotten today, SIGSALY was instrumental in securing ultimate Allied victory and a landmark in telecommunications technology in its own right, achieving a number of important firsts, including the first implementation of pulse code modulation, quantized speech transmission, multi-level frequency shift keying, and speech bandwidth compression, all of which are fundamental to the operation of modern digital communication systems. And in addition to revolutionizing telecommunications, SIGSALY and the vocoder have left another unexpected legacy in music. Starting in the 1960s and 70s, artists and musical groups like Nucleus, Africa, Bambaataa, Wendy Carlos, and Kraftwerk began experimenting with vocoders to generate surreal, robotic-sounding vocals, creating an entirely new music genre in the process. So the next time you use your cell phone or the internet or listen to an electronic song, you have the Second World War to thank. Sorry, Edwin Starr, war is absolutely good for something.